Hello everyone, this is section 4.6 and we're looking at problem 297. 297 has a function y equals x cubed plus 4x squared plus 3x all over 3x plus 9. That is definitely a rational function, and we are asked to find local maximum, local minimum, any inflection points, and any asymptotic behavior. We're not supposed to have a look at the graph. So I'm going to go ahead and, it's there. You might have seen it just for a second. I'm going to cover up the graph and see if we can't duplicate this on our own. So the first thing you want to do with a rational function is let's identify the domain, and we can't have the denominator go to 0, and that happens precisely at -3. In fact, I'll put the domain here of y. I'll use set notation, set of all x such that x is not -3. Okay. Let's go ahead and factor this function in the numerator and the denominator. So in the numerator I factor out an x, leaving x squared plus 4x plus 3. In the denominator I'll factor a 3 out. Continue to factor the numerator, x plus 3, x plus 1, and I have 3 over x plus 3. So it looks like I have the x plus 3's in the numerator and denominator that are common factors that can divide. And so my function reduces nicely to x times x plus 1 divided by 3, and I can essentially write out 1/3 out here. I am going to note that x cannot be -3. So for all practical purposes, this looks like a parabola. You can go ahead and distribute the x if you want. So the function is going to be 1/3 x squared plus 1/3 x, and x can't be -3. Notice the zeros are easy to find because if I look at the factored form here, here x equals -1 and x equals 0 will make the whole function go to 0. So the zeros are simply at x equals 0 and x equal -1. Okay, it's undefined at -3. If I try to find local minimums and local maximums, I do know it's a parabola, so I could essentially use the vertex formula. But let's say that we forgot the vertex formula and we just totally forgot how to complete the square to find the vertex. And so we could take the derivative of this, and so the derivative is 2/3 x plus 1/3. And now we just need to find when the derivative goes to 0. It's well defined here for all real numbers. We do know that x can't be -3, so we'll set that to 0 to find the critical numbers. I could simply multiply everything by 3 here. And here we see x equals -1/2, the critical number. Okay, now we could use the first derivative test. In fact, maybe I'll show us the first derivative test to determine if that critical number is resulting in some type of local minimum or maximum. So here's my critical number. Remember, we need to draw a number line here. Put our critical number here at x equals -1/2. And so that's where the derivative goes to 0. We would like to know what happens on either side of that critical number. So I could use a test point. Let's say f prime at, how about 0? And f prime at 0 will be 2/3 times 0 plus 1/3. And all I really care about is the sign. Yes, f prime at 0 is 1/3, but all I need to know is that it's bigger than 0. So over here, it's positive. At x equal -1/2, the derivative was 0. Let's test over here on the left-hand side of -1/2. How about f prime at, let's say, -1? So f prime at -1 equals 2/3 times -1 plus 1/3. It's -2/3 plus 1/3, which would be -1/3, which we know is less than 0. So I know the derivative over here is negative. So it's going from decreasing, decreasing, decreasing. So decreasing, 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 decreasing. At x equals -1/2, it's now 0, and then increasing, 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 increasing. And so we can easily see that -1/2 will result in a local minimum. So x equals -1/2 will give me a local min. Of course, we could find the vertex here. If I put -1/2 all the way back into the function here, and I'll use the factored form of it right up here. So I'll use 1/3 times -1/2 times -1/2 plus 1. So y at -1/2 equals 1/3 times -1/2 times -1/2 plus 1. And so here I'm going to get 1/2 times -1/2 will be -1/4 times 1/3 will be -1/12. So this is going to be -1/12. So putting that together here, we've got the local min at -1/2, -1/12. Now that was using the first derivative test, which is effective, but maybe that takes too long for us. Well, we can use the second derivative test. So I'm going to rewrite the first derivative. We got 2/3 x plus 1/3. And taking one more derivative is easy enough to do. It's 2/3. So what you do is you take the second derivative and evaluate it at the critical number. So this is going to be y double prime at -1/2, which is, well, y double prime is just 2/3. It doesn't really care what the input is, so it's 2/3, and that's always positive. So the second derivative is positive at the critical number, and so that means it's concave up. And if it's concave up, that means the critical number had to result because it became a local minimum. So right there would be the local minimum. So with the second derivative test, it's much quicker because the second derivative is easy to compute, and the second derivative evaluated at the critical number is positive. So therefore, by the second derivative test, -1/2, -1/12, a local min. Now we don't need to check for any type of asymptotes here because we do know the behavior of a parabola. So what we have here is it's not defined at -3. We have a local minimum at -1/2, -1/12, and we also found that there are zeros at 0 and -1. So maybe I'll highlight that because it is somewhat important here. So zeros at 0 and -1. It's undefined at -3. And we have a local minimum at -1/2, -1/12. So that's using strictly and purely analytic methods. Let's go and look at the graph of this. And you can see here it's not defined at -3. It's got a 0 at -1. It's got a 0 at 0. And I guess if I zoomed in, the local minimum would be at -1/2, -1/12. And that completes this problem.